If a plus b plus c is 0, if you had to draw that, what would you see if you drew that? If you drew a plus b plus c is 0, raise your hands. If you drew that, what would you see? What would you see, Chip? Yeah, exactly. You would see a plus b is c. You would see a what? You would see a triangle, right? In order to form a triangle, so it's if that's true, and if that's true, okay, where do all of those three? I'm trying to ask this without giving away the answer. Where do all three of them live? One plane. So they are what? Coplanar. They are all on the same plane. They live in the same plane, right? So there's a plane that extends, right? What does it mean? What does A cross B mean? Can someone just tell me, what does A cross B mean? What is that in relation to A and B? It's the cross product, but what does it mean geometrically and algebraically?
Magnitude of A times magnitude of B sine theta.
So no, I mean, is it a scalar? Is it a vector? It's a vector perpendicular to the parallelogram formed by A and B, right? So where would that be? It would be like this, right? It'd be perpendicular, right? And what can you tell me about the magnitude of that vector? It's the area of the parallelogram formed by A and B, right? Where are the other three vectors? Well, the other crosses are all going to be like this, right? So does this statement kind of make sense in a way? But how do you prove it? How do you prove that? Anybody have an idea of how to prove that? Yeah.
Write the first line in terms of C.
Yeah, exactly. Good. So you saw that, yeah. So you take this and you say, and you could pick any of the other ones, but C is kind of a good choice. C is going to be equal to what? Negative A plus B, right? And then what do you do with that? What do you do with that once you've isolated C?
You can say that's A. You can cross it with.
One of you, go. No, Soma, go. What would you do?
Cross it with B.
Yeah, you could take this right here. Can you still see the writing? Okay. Where would you put that? Put it right there. So if we actually did that, let me see if I can get a little bigger here. Yep, there we go. If we actually did that, we do B cross C is actually going to be B cross what? Negative what? A plus B, right? And then you need to remember your vector and cross product rules. So the first thing you can do is, what do you think you can do with that negative sign? What do you think you could do with that negative sign? What could you normally do with negative signs? Yeah.
You can bring it outside.
Yeah, you can bring it to the front. So it's negative B cross A plus B, like this. And do you remember what you do with cross products in terms of parentheses? We had a list of rules, like what you're allowed to do. Yeah, you can distribute. You can effectively treat cross products just like treat multiplication, which makes it all the more confusing. So what do you end up with? Negative what? Yeah, you could do B cross A plus what? B cross B. What is a vector cross itself?
0.
It is 0, exactly. It is 0. Now, I think, in my opinion, this is the trickiest step. You're now left with negative B cross A, like this. What might you be tempted to do, which is not what it equals? What might you be you might be tempted to distribute the negative sign, right? But what does negative do? It flips the direction, but we know that how you do that by changing the order of the cross product, changing the order of the cross product. So what does this actually equal? A cross B. So what have we now proven? We've proven that B cross C is equal to A cross B. And then what we do is we do the same thing where we plug that into the C right here. You prove a similar statement and then you're done. What does this prove geometrically? Well, it proves, see the red vector there? That was A cross B, right? Where is the parallelogram? The parallelogram that is equal, the magnitude of that vector is equal to the area of this parallelogram right there. You see that right there? There are 3 other parallelograms you can form with the other pairs. So for example, let's say we made this one blue. What's the parallelogram that's formed with these? It would be this parallelogram, right? So there's that. Is there a third parallelogram you can draw? Yes. What is this proven? This proves that all 3 parallelograms have the same what? Have the same area. So if you draw a triangle and form the 3 parallelograms that are formed by any 2 pairs of sides, you will always get the same area. Does that kind of make sense? Yeah. Cool. It's kind of a neat thing to be able to prove. It's also proven in such a way that it's still true in 3 space. Like our proof methodology doesn't just work in 2 space; it works in 3 space.
Oh wait, is the third one the AC one?
The AC one. I didn't draw it in there. It gets really busy. Remember, I think one of the things I told you first off was that the more lines you draw in a three-dimensional diagram, all of a sudden it goes and it loses all perspective.
Oh wait,
It's kind of cool.
it's just because you're multiplying the area by 2.
Well, look, careful. Like, so look, let's say you had a triangle like this. What are the parallelograms that you can draw? Well, you could draw, let me see if I can draw this not bad here. So there's this one, right? Which is like that one, right?
Yeah.
And then let's draw another one. So then there's this one, like this. I'm doing a terrible job at this. I'm very sorry. Like that, right? There's this parallelogram, right?
Yeah.
And then there's one more, right? Which is this.
Yeah.
All of those parallelograms have the same area.
But it's
Cool.
because they're multiplying the original triangle by 2.
It doubles it. Yes. Yes. Yeah. Oh, why? That is absolutely correct. Good observation, Soma. Yeah, you're folding it over each direction. Yeah, that's good. That's a good way to, I like that. Three folds. Okay, so what does this say? It says if A is this and B is that and C is that, and those are not esoteric new representations. Those just are general forms of three vectors, right? A1, A2, A3. Yay. You show that this is true. You show this is true. It's similar to proving a trigonometric identity. You work on one side and then you try to turn it into the other side. Which side do you want to work on? The left-hand side or the right-hand side? You want to work on the left-hand side? Okay, so Andy, if we work on the left-hand side, what do we need to do first if we're going to work on the left-hand side? Yeah, do B cross C first. If you're going to do B cross C, you have to set it up. What goes across the top? I, J, and K, and then it's going to go B1, B2, and then C1, C2, and C3. Now, when we've done this out in class, how have we done it? We've circled I, right? Crossed it out, and it's equal, so what was it? I times what? B2, C3, yep.
Minus B3,
C2, and then the trick was it's negative J times what? Then you erase this, right? Yeah, you do these two instead, and you get what? B1, C3 minus C1, and then you get K times B1 what? B1 C2 and C1, right? Okay, so you look at that and you're like, okay, what is that? Well, that right there is a vector that you then need to dot product by A, right? What is the vector A? The vector A is A1, comma, A2, comma, A3, and you're dotting it by this vector. What is this new vector? Well, B2, C3 minus B3, C2, right? Comma what? Negative B1, C3 minus B3. You see, I'm just writing this out, and it's kind of annoying to write out this way, but it's one way to do it. There's other ways. Are you with me so far?
Yeah.
With me so far? Excellent. So when you dot product, what do you do to find the dot product of two vectors? You multiply the corresponding terms and you add them together, right?
Yeah.
So what would the dot product look like? It would be A1 times what? B2 C3 minus B3 C2, right? Minus A2 times what? B1 C3 minus B3, plus A3 times what? B1 C2 minus B2 C1, right? Okay, that right there is the dot product. That is a scalar, right? Those are all numbers, so that would be a scalar. Look at the board for a second. This right here should look very, very similar to something you've already written. What does it look similar to? It looks really, really similar to something. I'll give you a hint. Look, it's exactly the same as what we started with, except instead of IJK, what is it? A1, A2, A3. So what is this actually equal to? It's the same as what we started with, but instead of IJK across the top, what is it? A1, A2, A3, B1, B2, B3, and C1, C2, C3. If you look this up in the book, do you know what they do instead? The way they make this a little bit more explicit, how do you write this? That right there is what? That is B2, B2, B3, C2, C3. With the bars, that means the determinant of that little thing. Does that make sense, everybody? They just want you to show you structurally that's what it is. The scalar triple product. The scale. So what does that mean? If you want to find the volume of a parallelepiped, if you want to find the volume of a parallelepiped, what do? You just do this. Multiply it out, and you're done. This is scalar triple product. This is a definition for it right there. It just allows you to kind of glue it together a little bit. That's it. It just allows you to glue it together. Remember, this all works too in 2 dimensions. So let's say I had two vectors here. Can you find the area? If I gave you two vectors, just a quick question for you. Let's say the vector v was, I don't know, 1, 4, and vector w was, let's say 2, 6. If you put those end to end, you could create a triangle, right? You could, any two vectors creates a triangle. What's the area of that triangle? Do not write anything down. What's the area of that triangle? Don't do it by writing anything down. How do you find the area of that triangle? It would be 1/2 of 1, 4, 2, 6, or you might have done 1/2 of what? 2, 6, 1, 4, right? What do you get here? 1/2 of 6 minus 8, or 1/2 of what? 8 minus 6. But when you do the determinant, what are you taking? You need to take you have negative 1 there, and you have what down here? 1. So you take the absolute value, so the area is going to be 1. What's kind of cool is when you're taking these areas, so if you use integer values for your vectors, the area of your triangle at most is going to be in terms of a half. You can't get any other decimal besides a half, which is kind of cool to think about, right? Because when you multiply integers and subtract them, you're always going to get an integer. Divide by 2, the worst you can get is a half. It's kind of cool to think about. Jared, did you